All right, so we want to look at the last type of application problem that we'll look at, and this is a mechanics problem, not a car mechanic, but officially they're called Newtonian mechanics, something, an object in motion. And so let's just review a few ideas about what you already know. And I'm not a physics teacher, so I apologize if you are, and feel free to send us a message and add to the discussion. So there's a couple of formulas that we want to think about. So the basic formula that we learn in physics is that a force is equal to mass times acceleration. That actually is going to be our kind of our overarching formula today that we want to work with. But there's lots of implications that goes along with that. Weight. If you get on the scale, your weight is actually a force. So weight is equal to your mass times the acceleration due to gravity. So these problems may say an object weighs something, in which case you're going to ultimately need mass. These problems may say it has a mass of something, in which case you may need to solve for weight. So be able to do that either way. This acceleration due to gravity, that value is constant, but it hinges on what measurement system I'm using. So in standard units, if I'm using pounds, then the acceleration due to gravity is a negative 32 feet per second per second. Negative 32. If I'm in the metric system, if I'm using, say, kilograms or something of that nature, then my acceleration due to gravity is a negative 9.81 meters per second. So each second that goes by, it speeds up an additional 9.81 meters, or it speeds up an additional negative 32 feet. So we're trying to model today objects in motion. And so if I go back and think about some Cal 1 ideas, in Calculus 1, if we have a position function, and I apologize in advance, I tend to swap back and forth between notations. In our calculus book that I normally use, S of t is a position function, but I will tell you that I've used x of t also as a position function on some of these problems, so don't let that throw you off. I'll just do that as a thought over here. So if I differentiate position, I get an expression for velocity. If I differentiate velocity, which is the second derivative, I get an expression for acceleration. So what we're looking at today is this idea of the change in velocity, which ends up being an acceleration kind of component. Okay, so if I'm trying to model acceleration due to gravity in this instance, that's the same thing as the change in velocity with respect to time. And so just let those ideas kind of circulate around. Remember, I'm writing a differential equation, so I'm going to need some differential there to be able to solve it. All right, the other thing that comes up on these problems is that the forces acting upon an object are equal. So I want to find the combination of all of these forces. So what does that mean for us? If I'm dropping some object, right, it has some mass and it's being acted upon in lots of ways, but it's acting upon by this acceleration component. So typically I have some mass times that acceleration component. And that's equivalent to all the other forces that are at play. What other forces might be at play? Well, there might be the weight of the object. I might need that. There might be air resistance. In Cal 1, we solved this problem, but we negate air resistance because it gets, and actually for us too, it gets really complicated to describe air resistance. If I'm on top of a mountain, the air resistance is different than the air resistance 100 feet above the ground, right? So we'll have some formula or whatever to be able to describe that. Maybe I throw the object, so maybe there's an initial force that's going on with that. So as we're modeling these things, we want to think about all these other forces that are at play. For our purposes, I've got this differential equation is ultimately the one that I want to think about. Mass times acceleration is equal to the sum of all these other forces. Depending on how things are operating is whether things are negative or not. So we'll say that a force going toward the Earth, we'll let that be a positive force, and a force that's impeding that, maybe this air resistance, or maybe if I throw the object up even, we'll let that be a negative force. So these may not be positive in here. It depends on how they're acting upon one another. All right, so that's a flying trip through some physics ideas. So we're going to need to know one of these two values depending on the units in the problem. I may need to solve for mass. I may need to solve for weight because I need both of those in my problem. I'm ultimately trying to model the change in velocity, and so I'll get an expression for velocity at time t, v of t, but I also may ultimately be interested in position, in which case I would need to integrate a second time. So you may want to pause this and go back and think about all of those ideas, but with all of those things circulating in our minds, let's look at lecture 10 and problem number 1. And there are, I believe, 5 problems in here. So whatever I don't work, please try those for homework. All right, so number 1 says a stone weighing 4 pounds falls from rest toward the earth from a great height. Height I don't know about. As it falls, it is acted upon by air resistance that's numerically equal to a negative 1/2 v, where v is the velocity in feet per second. And keep in mind feet per second, so that's going to impact what I do with some of these values. Okay, so several pieces here we need to get. A stone weighs, the weight is 4 pounds, which means its mass, I'm not going to worry about the sign there, that'll come into play in a moment. But its mass is 4 over 32, or 1/8. So a weight of 4 pounds is equivalent to a mass of 1/8. I believe the unit is slugs, but again, we're not going to worry too much about the units. Falls from rest. Well, what information does that give me? If it starts from rest, that means the velocity at time equal to 0 is 0. So I might need that. A great height, that doesn't help me any, doesn't. I know air resistance, so that's one of those forces. And again, that's the one that I need to make negative because that's this object is falling, that's going to impede the fall, this idea of air resistance. All right, so it says to find the velocity and the distance falling at time equal t seconds. So here we go. My formula is mass times acceleration is equal to all of these other forces at play. I know the mass. I'm trying to describe acceleration. I'm trying to describe ultimately velocity, but this represents acceleration. So what forces are at play? Well, I've got the weight of the object, and then I've got air resistance. So this is the formula, the differential equation that ultimately I want to solve. And let's see, I think I'll multiply through by 8. And, just thinking ahead, it may be linear. So I'm left with 32 minus 4v. 32 minus 4v. So it is a linear function, and you're welcome to solve it using that technique. I tell you what, I think I'm going to divide both sides by 32 minus 4v and multiply both sides by dt. So let that algebra work out for you. But this ends up being 32 minus 4v under dv equal to dt. How do I decide what to put where? Keep in mind what I'm trying to model, in this case velocity. So ultimately I want a velocity function on this left hand side. All right, and so I believe that's going to integrate into a natural log. You can go through your u substitution there. And the integral of dt is just t plus a constant. So it looks like I can multiply through by negative 4. Negative 4 times a constant is still a constant. We've talked about that numerous times. I can exponentiate. And we've played that same game lots and lots of times. You can go back and look at previous work to simplify that. So let's see, maybe I'll subtract 32. And finally divide through by negative 4. On those, sorry you can't see that, on those temperature problems I swapped that, but it doesn't really matter, does it? And a constant divided by negative 4 is still a constant, so don't be thrown off by that. So, do I have an initial condition? Yes, this object fell from rest. So let me pick this initial condition that says the velocity at time equal to 0 is 0. Which says c must be negative 8. Which tells me then that the velocity at any time is negative 8 e to the negative 4t power plus 8. This function models the change in velocity at any time t. And we want to also model the distance formula. So I need to integrate this again and to find the distance. So this is the change in position with respect to time, is another expression for velocity. It's making use of this idea. I have found velocity, but that's the same thing as saying the derivative of position. So ds dt. And so I would integrate this formula with respect to time. Right, so I can multiply both sides by dt and integrate. I've got a constant there, and I'm not seeing anything unless y'all do. Let me look at where I've worked this problem previously. I'm not seeing anything in there. With an initial condition for position. So I tell you what, let's just find the velocity at each of these times. Unless y'all see something that I'm not seeing. I don't know if I've mistyped that problem. Let me look in this book real quick. Bear with me one moment. Actually, that's in another book that I've put back on the shelf, so that's fine. We won't worry about position. So the second part of that problem says to find the velocity after 5 seconds. So you'll just find v of 5, and it's about in the neighborhood, I'll leave that for you to do the calculation, about in the neighborhood of at 8 feet per second. Oh, I do know about that's the answer to B part. Let me go back and deal with distance again. I think I do see what to do there. What I could do is to calculate when the velocity is 0, meaning this object is falling. Excuse me, when it hits the ground, that's when the velocity is 0. I could see what time that is, and I could use that as a condition to solve for C. But again, I think let's just be satisfied with the idea of velocity. Okay, so that's number 1. Look at let's see, there was one more I wanted to work that was, I think number 2 works similar to that, but it's thrown vertically upward. So when you model that to begin with, that throwing that object up, that first force is going to be negative. And it weighs 3/4 of a pound, so it's 3/4 of a pound going down. It's a negative 3/4 of a pound if it's beginning to travel up. So just keep that in mind. So your formula there, you'll need to, of course, calculate the mass based on this weight. I calculated that mass on a problem, and I got, if the weight is 3/4 of a pound, that's 3/4 times 32 m, and that's going to be 3/128 for your mass. But that first force, the ball is thrown upwards, so a negative 3/4, and air resistance is acting upon that, and so a negative 1/64 times V. So see if you can solve that problem. I'll have some solutions for that later in the week. Okay. Let's see, is there one, maybe a different unit? Yeah, look at number 16. An object weighing 16 pounds. So let me just pause right there and think about the fact that weight is, again, mass times acceleration, mass times 32. It looks like that's going to be a mass of 1/2. And again, I think the unit there is slugs. So 1/2 the change in velocity with respect to time, and we hadn't even finished reading the problem, have we? Is dropped from rest on the surface of a calm lake and thereafter starts to sink, while its weight tends to force it downward. So you've got a force of weight, you've got a second force going on. The buoyancy of the force is 6 pounds, and it's a negative 6, isn't it? Because that weight is going down, but that buoyancy force is causing it to slow down, or is impeding it. And then you've got the resistance of the water, so you actually have a third force going on. Resistance of the water is numerically equal to twice the square of velocity. So a negative 2v squared. So your differential equation here looks like 16 minus 6 minus 2v squared. So 3 things going on here, and that's okay. So 1/2 dv dt, and y'all, I can combine those, so that's not bad at all. And I can multiply through by 2. So 20 minus 4v squared might be the best formula to try to solve there. I'm just thinking ahead because that's square root might be more problem than I wanted. I just picked a problem as I always do. And yes, so I'm going to post a solution here, but when you this is what I'm going to integrate, right? We've used that same kind of function a couple of times. This is no longer a du over u case because my u is 20 minus 40v squared. So that is going to cause me a problem, and I didn't even realize that when I worked that problem. So let me just think about that for a moment with you. We could use partial fractions or something to solve that. Again, I just picked some problems and put on this handout. I didn't think about how they're going to work, but I'll give you a solution to that. Let's just say for this problem, if you can get to the model, we would assume that we would have some techniques to be able to solve that. Number 4 is pretty straightforward. Number 5, that's the other one I want to think about because my units change, and it says an object of mass 5 kilograms. So I may need the weight. And so the weight of the object here is mass times the acceleration. And again, I'm in the metric system this time, so that's what's going to change for that, whatever that value is. What else is going on? You got an initial velocity of 50 meters per second. And it's so you not only have this weight traveling, you've got some force behind it, and you've got air resistance going on. So I think this is still going to be, three forces at play: the weight of the object, the initial velocity pushing that further, and then the air resistance that's slowing that down. So see if you can model that. I'll post solutions to each of these. Hopefully the integration to the rest won't be nearly as bad, but it'll be later in the week before I do post those solutions. So keep that in mind. All right, let me know what questions that you have.